It's one of the great paradoxes in how things work. Systems that are meticulously optimized for success often carry the seeds of their own collapse. So, in this explainer, we're going to examine the underlying mechanics of this process, really get into how the relentless drive for peak efficiency can systematically create a deep, hidden fragility.
You know, we tend to assume that efficiency creates strength. A streamlined, highly optimized system, well, it just seems robust by its very nature. But when you look closer, it turns out that the most efficient systems are often the most fragile, incredibly vulnerable to a sudden, catastrophic failure the moment conditions change.
So, to really understand this paradox, we're going to break down the relationship between efficiency and fragility. We'll look at the paradox itself, what makes a system successful to begin with, the tug of war between optimization and adaptability, how success can lead to rigidity, where that weakness is structured, and finally, why this trade-off seems to be inevitable. Okay, first things first, we need to establish a clear framework for how different systems react to volatility and shock, because they don't all respond in the same way.
A fragile system is pretty straightforward. When it's exposed to stressors, to shocks, to any kind of randomness, it degrades or breaks. Its performance actually gets worse under pressure. Then you have a robust system. This one, in contrast, is built to withstand shocks. It remains largely unchanged. It's designed to resist a certain level of stress and just keep functioning.
And then there's a fascinating third category, the anti-fragile system. This is a system that doesn't just resist stress, it actually improves. It learns from shocks, it grows stronger from volatility.
Now, the key characteristic of a fragile system isn't just that it breaks, but it's the shape of its response to stress. The harm isn't linear. In fact, small stressors can cause accelerating, completely disproportionate damage. This is what we mean by a concave sensitivity. On the flip side, an anti-fragile system has what's called a convex benefit profile. It gains more from a big positive shock than it loses from a similar negative one. It thrives on volatility. Our focus, though, is on how optimized systems start to drift toward that fragile, concave profile.
So, any successful system, really, it operates according to an internal logic. You can think of it as a success formula that's built from 5 key interlocking parts. First up, you have strategic frames. These are basically the mental models that define everything: the environment, the competition, how value gets created. It's the system's fundamental map of the world. Second, you've got processes. These are all the routines, both formal and informal, the workflows that structure all the activity and reliably turn inputs into outputs. Third, resources. This includes the obvious tangible assets like technology and infrastructure, but also the intangible ones, like brand reputation or a very specific kind of expertise. Fourth are relationships. These are the established connections the system depends on to survive, with partners, suppliers, users, all those essential external actors. And finally, values. These are the core principles that give the system a collective identity. They're what guide decision-making, especially when things get ambiguous. A system gets efficient by taking that success formula we just talked about and relentlessly optimizing it for a very specific, predictable environment. But this optimization, well, it creates a fundamental trade-off. To maximize its performance, the system has to narrow its focus. It perfects its frames, its processes, its resources for just one set of conditions. And this refinement, by its very definition, shrinks its capacity to respond effectively when conditions are different. So efficiency is gained, but it comes at the cost of flexibility. Now, over time, as the system succeeds again and again, its belief in its own formula gets reinforced. Its components start to harden, transforming from sources of strength into sources of rigidity. This process is known as active inertia. So those strategic frames, which were once a source of incredible clarity, they become blinders. The system starts to filter out any new information that doesn't fit its established worldview, effectively ignoring new threats and new opportunities. The effective processes, the ones developed to solve very specific problems, they calcify into mindless routines. They just get performed without question, even if the underlying problem has completely changed. And those key relationships that once guaranteed success, they become shackles. The system gets locked into dependencies that prevent it from pivoting or exploring new alliances, even when its own survival might depend on it.
This whole hardening process creates a very distinct structure, and if we visualize the system as a network, we can actually see its hidden vulnerability. See, a less optimized, maybe more redundant system might look like a random network. It's kind of messy, but the connections are distributed pretty evenly. A highly efficient system, though, tends to evolve into what's called a scale-free network, which is characterized by a few critical hubs that handle almost all of the traffic. Now, this efficient, scale-free structure is extremely robust against random errors. If you remove a minor, peripheral node, well, it has almost no effect on the network's overall function. The system appears incredibly strong. But this is where the fragility is exposed. That same system is acutely vulnerable to a targeted shock. If you remove just one of those central hubs, the entire network can fragment and collapse. The system's efficiency has created a critical, single point of failure. And this brings us right back to the resolution of our initial paradox, that observation that efficiency somehow seems to create fragility. It turns out fragility isn't a mistake or a flaw in the design. It's the logical, emergent consequence of a system becoming perfectly adapted to a single, stable state of the world. The very act of eliminating redundancy is the source of both its efficiency and its brittleness. Ultimately, what this means is that the pursuit of maximum efficiency is a deep commitment to a narrow set of assumptions about how the world works. That intense focus is precisely what makes the system successful, but it's also what makes its collapse almost inevitable when those assumptions are no longer true, and the environment fundamentally shifts.